Good afternoon. Yeah, good afternoon. This is the week 10 of the live interactive session for the NPTEL course Introduction to Atmospheric and Space Sciences. So for the last few classes, we have been discussing about the stability of the atmosphere, different types of lab rates we saw like dry adiabatic, moist adiabatic, saturated adiabatic, etc. And also we discussed about what are the different conditions when the atmosphere is said to be stable, unstable, and neutral. So these things we have been discussing in the last class. So today we will be mostly discussing about cloud formation. What are the process of cloud formation, um, and like some parts of an introduction to the ionosphere and its different layers. So we know that the clouds form when air is so if you remember, we discussed about the air parcels being saturated as the air parcel is vertically moving up in the air due to the decrease in pressure. The air parcels expand, it will adiabatically cool and it will become saturated. Once the air parcel becomes saturated, condensation will start to begin in the parcel. So that's what we have been discussing till now. So clouds generally form when air becomes supersaturated with respect to liquid water. Supersaturated in the sense the parcel is holding it has exceeded the saturation level. So that is basically what is meant by supersaturation. So the vapor pressure is greater than the saturation vapor pressure. So supersaturation is reached in the atmosphere and most by the ascent of air parcel, which results in the expansion of the air and adiabatic cooling. As the air parcel is vertically ascend in the air, that's how generally the air parcels reach supersaturation. And at this stage, when the parcels become supersaturated, the water vapor condenses and then forms small water droplets or ice particles. So basically, the clouds form when air becomes supersaturated with respect to liquid water. And supersaturation is reached in the atmosphere through the vertical ascent of air parcels. Through the vertical ascent of air parcels, which results in the expansion of the air and adiabatic cooling. So when the parcel becomes supersaturated, the water vapor condenses to form a cloud of small water droplets or ice particles. So we have learned like as the parcel is vertically moving up in the air, initially it will reach a level known as the lifting condensation level where the parcel becomes saturated. And above that level, we told that the parcel is saturated. So if we again raise the parcel above the LCL, it starts condensing. And when we also learned about level of reconduction. Now we will be mostly discussing how this condensation has happened. What are the process of condensation? So there are two methods or two processes in which generally the clouds are formed. First one is the homogeneous nucleation. Cloud formation, and we discuss cloud formation. There are two types. First one is homogeneous nucleation. Homogeneous nucleation in the sense the cloud droplets are formed by the chance collision between homogeneous nucleation is basically the chance collision water droplets, chance collision of water droplets in the vapor phase to form small embryonic water droplets that are large enough to remain intact. So there will be a large number of water vapor molecules. These vapor molecules collide with each other, and during the collision, the condensation occurs. Then they form water droplets. So the size of these water droplets will be generally very much small, and it will be very difficult for these water droplets to survive. Which means once these droplets are formed, they will immediately evaporate back into the vapor phase. The stability of these water vapor molecules, the survival will be very less because it will be very small. The size of the water droplets will be very small. So for droplets that form through homogeneous nucleation, uh, for it to remain intact, there is high levels of supersaturation is required for its formation and survival. So if the droplets are forming by the chance collision of water vapor molecules, um, then in that case, for the water droplets that is formed by this method, for them to remain intact, high levels of supersaturation is required. High levels of supersaturation is required for the formation and survival of these droplets. So in natural clouds, the droplets do not form by homogeneous nucleation because of this condition, because they need very high levels of supersaturation. Because of that, in natural clouds, generally the droplets do not form by what is known as homogeneous nucleation. So droplets do not form in natural clouds by the homogeneous nucleation. of pure water droplet. So homogeneous nucleation, there is no external agency involved. Just the pure water vapor molecules collide with each other and they form very small embryonic water droplets by the chance collision between the water vapor molecules. So the chance of survival of these small water droplets are very much less, because for them to for their formation and survival, very high levels of supersaturation is required. Because of this, in natural clouds, the droplets generally doesn't form by homogeneous nucleation. Then how does this form? How generally the um, how generally is the water droplets formed in clouds? So there is another method which is known as process which is known as heterogeneous nucleation. So heterogeneous nucleation means the water vapor molecules condense on top of atmospheric aerosols. Atmospheric aerosols are very tiny solid or liquid particles that are present in the atmosphere, like small particles that are present in the atmosphere. So generally the water, so these uh, act as a medium upon which the water vapor molecules can condense and form water molecules. So with the help of an external particle, in this case the water droplet molecules are formed, different from in case of homogeneous nucleation. So in case of homogeneous nucleation, there is no external particle involved. The water vapor droplets are formed solely by the chance collisions between the water vapor molecules, and they will condense and form water droplets, but they need very high levels of supersaturation for their formation and survival. So in natural clouds, generally the droplets doesn't form by homogeneous nucleation. So there is another type of nucleation which is known as heterogeneous nucleation. In this case, the water vapor molecules condense on aerosols or cloud condensation with the help of an external particle, which is basically known as cloud condensation. Okay. So upon the particles known as cloud condensation nuclei, these water vapor molecules condenses and form droplets. So aerosols are basically um, tiny solid or liquid particles that are present in the atmosphere. The example are desert dust, then the black carbon, the ash particles and all that is emitted from industries or vehicular pollution, and all those things are examples of aerosols. Then sea salt is an example of aerosols. Then during volcanic eruptions also large quantity or large amount of solid particles are being released into the atmosphere. These particles remain in the atmosphere and they modulate the Earth's climate. So these particles, these tiny solid liquid particles that are present in the atmosphere is basically known as aerosols. A subset of these, not all aerosols, but a subset of these aerosols are capable of serving as senders upon which water vapor can condense and form droplets. And the droplets can form and grow on these particles at much lower supersaturation than homogeneous, for homogeneous nucleation. So a subset of aerosols, a subset of are capable of subset of aerosols are capable of acting as centers upon which subset of aerosols are capable of acting as centers upon which water vapor can condense and form droplets. So in these case, so droplets form and grow at much lower supersaturation, at much lower supersaturation compared to that like small lower supersaturation than required for homogeneous nucleation and required for homogeneous nucleation. So there are two types of methods in which clouds generally form. One is homogeneous nucleation and another is heterogeneous nucleation. Homogeneous nucleation is in the sense the water vapor molecules, the water droplets are formed by the chance collision of water molecules in the vapor phase. Um, in that case, the droplets needs very level of supersaturation for the droplets that are formed through homogeneous nucleation for the survival and formation of droplets. So generally in natural clouds, homogeneous nucleation of pure water doesn't actually occur, or the clouds doesn't form through homogeneous nucleation. Then how does it actually form? There is another type which is known as heterogeneous nucleation. So in case of heterogeneous nucleation, there is an external particle that is serving as centers upon which the water vapor molecules can actually condense and then form the droplet. So in this case, the droplets can form and grow at much lower supersaturation than that required for homogeneous nucleation. So these particles that act as centers upon which water vapor can condense is basically a subset of aerosols that is present in the atmosphere. And these subset of aerosols that can actually act as centers upon which the vapor molecules can condense is basically known as cloud condensation nuclei. So three things. One is what is homogeneous nucleation, then heterogeneous nucleation, then cloud condensation nuclei. Three new terms we just So in case of cloud condensation nuclei, there are so as I said, a small subset of atmospheric aerosols that can serve as particles centers upon which water vapor can condense are basically known as cloud condensation nuclei. These particles are basically known as cloud condensation nuclei. So larger the size of the particle, more readily it is wetted by water, and the greater is its solubility, and lower will be the supersaturation at which the particle can serve as cloud condensation nuclei. So it is if the particle larger the particle which is acting as cloud condensation nuclei, higher is the chance of this condensation and formation of droplet. So, for example, to serve as cloud condensation nuclei at 1% supersaturation, the radius of the particle should be at least 0.1 micrometer. There are particles which is wettable, and there are particles which is which basically dissolves when water vapor condenses on it as well. So if we look at the aerosols that are present in the atmosphere, so I told you what are aerosols. Aerosols are small, tiny solid or liquid particles that are present in the atmosphere. Examples are desert dust, sea salt, and the pollutants emitted from vehicles, industries, and volcanic eruptions, etc. So the atmosphere contains particles that range in size from sub-micrometer to several tens of micrometer scale. So those particles that are vegetable can serve as centers upon which water vapor condenses. So among these aerosols, there are particles which are vegetable, or we can say hydrophilic or vegetable, and there are particles which are hydrophobic or unvegetable. What does it mean by hydrophilic and hydrophobic? Hydrophilic in the sense the particles allow water to spread out on it, as a horizontal film. There is a particle and if water vapor comes and condenses on it, it allows the water to um, spread out on the top of the particle and then form a horizontal film kind of thing. And in case of hydrophobic aerosols, water forms spherical droplets on its surface. Water forms spherical droplets on its surface. And some of the particles in air are soluble in. So among the hydrophilic, so these hydrophilic aerosols generally act as cloud condensation nuclei. Cloud condensation nuclei is basically a subset of aerosols which can act as centers upon which the water vapor molecule can condense and then form water molecules. So among these hydrophilic aerosols or the aerosols that act as cloud condensation nuclei, there is another subset which is actually soluble in water. Some of these particles are soluble in water as well. So they dissolve wholly or in part when water vapor condenses onto them. Either it will dissolve completely or partly when water vapor condenses onto them. And it will basically form a solution. Okay. So homogeneous nucleation, heterogeneous nucleation, water aerosols, two types of aerosols, hydrophilic and hydrophobic. Hydrophilic is vegetable, which means the particles allow water to spread out on it as a horizontal film. These hydrophilic aerosols generally act as the cloud condensation nuclei. And there are hydrophobic aerosols which are unwettable. So water basically, it doesn't allow the water to spread out on it, but instead the water forms spherical drops on its surface. And among the hydrophilic aerosols, there are some aerosols which are soluble in water as well, which means they dissolve wholly or in part when water vapor condenses onto them. So this, in case of water insoluble hydrophilic aerosols, in case of water insoluble, that is, it is vegetable but it won't dissolve. So in that case, to serve If there is 1% supersaturation, is supersaturation in the sense the relative humidity is 101%. Saturation is 100%. So 1% supersaturation means the relative humidity is 101%. So for a CCN at 1% supersaturation, completely vegetable but water insoluble particles requires a size of around 0.1 micrometer to act as CCN, or for allowing water particles to condense on vapor molecules to condense on. Whereas in case of soluble particles, so this is in case of insoluble particles, whereas in case of soluble particles, even a particle of as small as 0.01 micrometer can act as cloud condensation. Or even if a particle is of that small size, water can come and vapor molecules come and condense on. So this is in case of water insoluble particle, whereas in case of water soluble particle, at 1% supersaturation, even if the radius of the particle is 0.01 micrometer, that is 10 order magnitude less. So in case of soluble particles, if the supersaturation is 1%, even if the radius is 0.01 micrometer, it can act as cloud condensation nuclei. So if it is insoluble, the particle must be of size of at least 0.1 micrometer for it to act as cloud condensation nuclei. Whereas if the particle is soluble in water, in that case, at the same level of supersaturation, even if the particle size is 0.01 micrometer, it can act as cloud condensation nuclei. Okay. So basically most cloud condensation nuclei is a mixture of soluble and insoluble components. Generally, most of the cloud condensation nuclei, most of the cloud condensation nuclei are a mixture of soluble and insoluble particles or components. So they are basically known as mixed nuclei. It has both a soluble component and an insoluble component. Yeah. So what all things we learned? We learned what is homogeneous nucleation. Homogeneous nucleation in the sense without the help of an external particle, the water vapor molecule, by the chance collision of water vapor molecules, the condensation occurs and water droplets are formed. But for the water droplets to form and survive through homogeneous nucleation, high levels of supersaturation is required. Then we learned what is heterogeneous nucleation. In case of heterogeneous nucleation, water vapor molecules condense upon some particles which act as centers upon which the condensation can occur. So during heterogeneous nucleation, one external particle is also, with the help of an external particle, this is happening. It is not a pure water droplet, so there will be these small particles within the droplet. So in case of heterogeneous nucleation, some particles in the air acts as centers upon which water vapor can condense. And these particles are known as cloud condensation. Cloud condensation. So this is basically a subset of aerosols. Subset of aerosols, namely hydrophilic aerosols. That is vegetable aerosols. Generally, the hydrophilic aerosols act as cloud condensation nuclei. So, in the hydrophilic aerosols also, there is insoluble and soluble as well. So, if the particles are soluble, then the condensation occurs more easily, whereas in case of insoluble particles, the size of the particle should be very large for condensation to occur. So as an example that I told, at one level of 1% supersaturation, if the particle is insoluble, then the particle size should be at least 0.1 micrometer for the condensation to occur or cloud formation to occur, whereas if the particle is soluble, even at that same level of supersaturation, the particle size is 0.01 micrometer, the condensation can occur. So it is more easy if there is hydrophilic soluble aerosols present in the atmosphere for the formation of clouds. Okay, so yeah, that is about different types of nucleation, different hydrophobic and hydrophilic aerosols. What is cloud condensation? Okay. Now let's see what is basically curvature effect. So during cloud formation, what are the things that we like for the cloud? Once the cloud droplet is formed, for it to grow, what are the processes that it has to undergo, and what are the issues that we generally face? So one type of effect is known as a curvature effect. So an ordinary cloud droplet will be extremely small, having an average diameter of 20 micrometer or 0.002 centimeter. Generally, when a cloud droplet is formed, size of the cloud droplet will be we are discussing curvature effect. So an ordinary cloud droplet, when it is formed, will be extremely small. So the average diameter of the cloud droplet will be 20 micrometer. Approximately it will be 20 micrometer. Whereas the size of the rain droplet will be 100 times. So this is basically very much small compared to that of the size of a rain droplet. The size of the rain droplet will be approximately 2000 micrometer. So this is the cloud droplet that is formed is 100 times smaller than the rain droplet. So all cloud droplets doesn't fall down as rain. Only some droplets after the formation they survive and then grow and reach this large size and then form as rain droplets. So all cloud droplets doesn't become rain. If a cloud droplet is in equilibrium with its surroundings, the size of the droplet does not change. So once the cloud droplet is formed and that cloud droplet is in equilibrium with its surroundings, the size of the droplet does not change because the water molecules condensing onto the droplet will be exactly balanced by those evaporating from it. And if the droplet is not in equilibrium, the droplet size, so once a cloud droplet is formed, this is the cloud droplet, it is having a size of approximately 20 micrometers. Suppose the cloud droplet is in equilibrium with its environment. The cloud drop doesn't grow, like it will stay in the size itself. because the amount of water vapor that is condensing to form the cloud droplets will be equal to the amount of water vapor that is evaporating from the cloud droplet. And if the cloud droplet is not in equilibrium, the droplet size either increase or decrease depending on whether condensation or evaporation dominates. So suppose consider a cloud droplet that is in equilibrium with its surroundings. The total number of molecules around the droplets remains fairly constant and defines the droplet saturation vapor pressure. So suppose this is a cloud droplet. So consider the droplet as in equilibrium with its surroundings. So the total number of water molecules around the droplet remains fairly constant and defines the droplet saturation vapor pressure. So what is the saturation vapor pressure on the surface of the droplet is determined by the number of cloud droplets that is present around the droplet. At equilibrium, the vapor pressure over a curved droplet of water is greater than that over the flat surface. So suppose there is a cloud droplet, it will be having a curved shape, right? And there is a flat water surface, the shape will be like this. So the saturation vapor pressure for this cloud droplet to be in equilibrium is higher than the saturation vapor pressure for this flat surface of water. Because of their curved surface, more water vapor molecules are required to maintain that shape of the droplet. So vapor molecules are less strongly attached to a curved water surface, hence they evaporate more readily. And also in a curved surface, if you look at the water vapor molecules over here, so this is attracted to these molecules. Right? Now when you consider a plane surface, there are a large number of molecules to which this droplet is attached. Or the cloud, it is more easy for the water molecules are basically less strongly attached to the curved water surface, hence they evaporate more readily. Whereas in case of flat surface, the water vapor molecules are more strongly attached to the nearby molecules. So evaporation happens more readily in case of a cloud droplet compared to that of a flat surface. So to keep the droplet in equilibrium, more water vapor molecules are needed around the water droplet to replace those molecules that are constantly evaporating from the surface. So constant evaporation will be taking place from the surface of the cloud droplet. So some water molecule is evaporating from it. There should be enough water vapor around the water droplet to compensate this. If water molecule is evaporating from it, there should be enough water vapor molecules that should condense back and then maintain the cloud droplet intact. So smaller cloud droplets require even greater vapor pressure to keep them from evaporating away. So larger the curvature of the droplet, different radiuses will be there. This is one droplet. There is one bigger droplet. So R2 is greater than R. So it will be easy to maintain this cloud droplet, or the stability of the cloud droplet with greater radius will be higher than the cloud droplet with a smaller radius. So since the radius R2 is greater than R1, the droplet with the higher radius will have more stability compared to that of the smaller droplet. Smaller cloud droplets require even greater vapor pressure to keep them from evaporating away. So what does it mean by vapor pressure? So if some droplet is evaporating from the surface of the cloud droplet, there should be vapor molecules that should immediately condense and then keep the cloud droplets intact. So so that basically shows the saturation vapor pressure. So in case of smaller water droplets, because the radius curvature is more, the water molecules are less strongly attached to the surface of the droplet as the curvature is higher. So it will more readily evaporate compared to that of the droplet of larger radius. So if you compare the saturation vapor pressure that needs for the droplet to be in equilibrium, in case of a larger droplet, the saturation vapor pressure required will be less, whereas in case of a smaller droplet, the saturation vapor pressure required is more. So smaller the droplet, the greater its curvature and higher the supersaturation needed to keep it in equilibrium. This is known as curvature effect. So the chance of survival of smaller droplets will be very less. Only once it becomes, or once the size of the droplet is larger enough, then only the chances of survival is more. Smaller the droplet, there is very less chance for the droplet to survive. For that droplet to survive, very large level of supersaturation is required. So you see this figure. So in this case, it basically shows the droplet diameter and the supersaturation level or relative humidity for the cloud droplet to remain intact. So as you can see, for smaller droplets, that is in case of a droplet, at 1 micrometer with a droplet diameter of 1 micrometer, the relative humidity is 100.2% or 0.2% supersaturation is enough for this cloud droplet, whereas in case of a droplet of size 10 micrometer, it is even less, like around 100% supersaturation or 100% relative humidity is enough for the droplet to survive. So for larger droplets, the amount of supersaturation required to keep the droplet in equilibrium is small, whereas for smaller droplets, very large level of supersaturation is required for the droplet to remain intact. So greater the curvature of the droplet, higher the supersaturation needed to keep the droplet in equilibrium. So this is basically known as the curvature effect. So as the droplet is becoming larger, the effect of curvature is decreasing. For a droplet whose diameter is greater than 20 micrometers, the curvature effect is so small that the droplet behave as if the surface is very flat. Just as relative humidity is less than that required for equilibrium, so basically, higher the curvature of the droplet, it needs very high level of supersaturation for the droplet to survive. Larger the size of the droplet or smaller the curvature, it requires very less amount of supersaturation for the droplet to survive. Now let's derive a mathematical expression for this curvature effect. So basically the curvature effect means smaller the droplet, the greater is its curvature and higher the supersaturation needed to keep it in equilibrium. So the chances of survival of smaller droplets is very small compared to the chance of survival of larger droplets. Smaller droplets need very high level of supersaturation for it to be kept in equilibrium, which means that it should survive. Like the rate of evaporation and rate of condensation should be similar. Equilibrium in the sense that only. So for a droplet to be kept in equilibrium, the droplet size is very small. It requires very large, high level of supersaturation. Whereas if the droplet size is large, uh, the surface more resembles to flat surface, and in that case, less level or smaller level of lower level of supersaturation is enough for the survival of the droplet or to keep the large droplets in equilibrium. Now the mathematical expression for the curvature effect. So this curvature effect is important because the droplet is spherical and shape. That is the reason why this curvature effect is actually coming into play. We know the droplets are actually spherical and shape. So there is a net inward force that holds the water droplet together. So there is some force that is actually holding this water droplet together in this shape. So that force is basically known as the net inward force divided by distance is known as surface tension. The net inward force divided by distance or area is known as the surface tension. The force that keeps the water droplet intact. So in case of a flat liquid surface, a molecule experience, yeah, as I told earlier, if we are considering a flat surface like this, the force that is experienced by this droplet will be higher compared to that of a droplet on a curved surface. The forces that is experienced by this water molecule will be lower compared to that of a water molecules on the surface of a flat liquid surface. It experiences more amount of force compared to that of a molecule in a curved surface. So in this case, more probability to escape. In case of a curved surface, the probability of more probability to escape. So rate of evaporation rate of evaporation is higher when the curvature is higher. So as the curvature is keeping on increasing and it is becoming more curved, the force that is holding the water molecules that is holding this particular water vapor molecule is kind of decreasing and decreasing. So the rate of evaporation is higher as the curvature is becoming higher. So basically the saturation vapor pressure over a curved surface of water would be larger compared to the plain surface of water. So that is basically known as curvature. The saturation vapor pressure over a curved surface, which means to keep that curved surface in equilibrium. The saturation vapor pressure that is required to keep the curved surface in equilibrium would be larger than compared to a plain surface of water because of the curvature. Plain surface of water is known as curvature. Now consider just give me a second. So consider a small tube of radius r from which it is basically vacuum. We have removed the air and now we have kept it in a liquid surface. Consider there is a small tube which is having a radius of r. We have removed air from it and we have kept it in a liquid surface. It has liquid. So as the time progresses, if we keep this tube inside if we keep it in the liquid surface, as time progresses, water will enter into the tube. Water will enter the tube and will rise to a height h. Water will start entering the tube and it will reach a height h. This height is h. Now we know sigma, so this will be curved, the surface will be curved. We know sigma is the surface tension. Rho L is the density of the liquid. Rho V is the density of the vapor. PL is the pressure of the liquid. And PV is the pressure of vapor. We know that the volume of the liquid is equal to mass by density. So we are basically going to see how the saturation vapor pressure over a curved surface, that is over here, saturation vapor pressure over here, E of R, is changing with respect to the saturation vapor pressure over a plane surface. This is Es of infinity because it doesn't have a radius, it is a flat surface, that's why we have kept it as infinity. So we are basically going to see how the saturation vapor pressure over a curved surface, Es of R, is changing with respect to the saturation vapor pressure over a plane surface, which is Es of infinity. So the volume of the water within the tube is given by pi r square. R is the radius, base area is pi r square, and height is h. So the volume of the water within the tube is given by pi r square h. The weight of air that has been replaced by the water, and the water entered the tube, the weight of air replaced by the water. Now, weight is basically mass into mg. Mass is density into volume. So density is basically rho L minus rho V into volume is pi r square h into g. That is weight. Pi r square h, rho L minus rho V into pi r square h into g. This is the weight of air replaced by the water. And since the density of liquid is very much greater than the density of water, density of vapor, we can write it as pi r square h rho L into g, because rho L is very much greater than rho V. Now we know sigma is basically the force per unit um, length. So 2 pi r, F will become 2 pi r into sigma. This is the force. Surface energy per force per unit length. F will become 2 pi r into sigma. So we can write 2 pi r sigma is equal to pi r square h rho L into g. Weight of the column over the liquid surface must be balanced by the surface tension at the meniscus of the tube. Weight of the column over the liquid surface. Over the liquid surface must be weight of the column over the liquid surface, and then this weight of this water column. Weight of this water column must be balanced by the surface tension at the meniscus of the tube. The force over here, which is acting, which is keeping that meniscus intact. Like here the force. So it should be equal. So 2 pi r sigma is the surface tension, and pi r square h rho L into g is the weight of the column over the liquid surface. it should be equal. So from this we can write H, the capillary, that height up to which the liquid column has raised, as H is equal to 2 sigma R rho L into H. This is the height up to which the liquid column has raised within the tube. Now the force balance at the surface of the membrane. So this is surface of the membrane. There is a pressure that is P1 minus P2. Delta P is given by P1 minus P2. So this is basically maintained by the force balance, which is known as the Laplace pressure, P1 minus P2. P1 is greater than P2. The pressure that is acting downward is basically greater than the pressure that is acting upward. So this Laplace pressure, or delta P, is basically balanced by a downward acting hydrostatic pressure. The Laplace pressure is basically balanced by Laplace pressure is P1 minus P2. P2 is acting upward and P1 is acting downward. So the Laplace, this is known as the Laplace pressure. The Laplace pressure is balanced by Laplace pressure is balanced by a downward acting hydrostatic pressure. So we can write dP by dz is equal to minus rho g. And if we are integrating from E of 0, which is the liquid surface, to E of h. So this is the vapor pressure at the surface, E of 0, and this is at the height E of h. So if we are finding the hydrostatic pressure, it will become E of 0 to E of h dP is equal to minus rho g into dz from 0 to h. We know from ideal gas law P is equal to rho RT. So we can write rho is equal to P by RT. So it will become integral E of 0 to E of h dP is equal to minus P by RTG to integral 0 to h dz. If we take the P to here, it will become integral E of 0 to E of h dP by P is equal to, the g is in the numerator, not in the denominator. If we take P to this side, it will become integral E of 0 to E of h dP by P is equal to integral 0 to h minus g by RT into dz. Or we can write log E of h by E of 0 is equal to minus g by RT into h, or gh by RT. E, or we can again simplify it into E of h is equal to E of 0 into exponential minus gh by r under equilibrium, right? E of 0 is equal to Es of infinity and E of h is equal to Es of h. So we can write Es of h is equal to Es of infinity into exponential minus gh by r. We know h is equal to 2 sigma by rho L G into R. That's what we found out first, the height. Height we found initially as h is equal to 2 sigma by R rho L into G. Now if we substitute that, it will become Es of R Es of R is equal to Es of infinity into exponential 2 sigma by R rho L R into this is the mathematical expression for the curvature. Es of R is equal to Es of infinity into exponential of 2 sigma by R rho L into R T. How the Es of R, the radius of the saturation vapor pressure of a droplet of size of radius R is changing with respect to the saturation vapor pressure over a plane surface. This Es of infinity. That's what it basically is. So this is a mathematical expression for curvature. Now there is something else called Raoult's law or Raoult's effect. So I told you earlier that some of the particles in air, some of the cloud condensation nuclei are soluble in water. So they dissolve either wholly or partly when water condenses onto them. So that a solution rather than a pure water droplet is found. So the saturation vapor pressure of water adjacent to a solution droplet is less than the saturation adjacent to a pure water droplet of the same size. So what does Raoult's law say? Raoult's law says that the saturation vapor pressure of water adjacent to a solution droplet. Solution droplet in the sense the cloud condensation nuclei upon which the water vapor condenses to form water droplet basically dissolves in the water. So now instead of a pure droplet we have a solution droplet with the cloud condensation of so the saturation vapor pressure of water adjacent to a solution droplet is less than adjacent to a pure water droplet of the same size. So there is, and I told you earlier, if there is a particle which is capable of dissolving in the water when the vapor is condensing on it, then it, even if the particle is very small, the chances of that droplet to survive is very high. whereas if the particle is not dissolving, it is remaining like as it is, then the size should be very large for the particle to survive. So even at same levels of supersaturation, we saw that in case of an insoluble CCN, it should have a radius of at least 0.1 micrometer for it to survive. Whereas in case of a soluble, the size 0.01 micrometer size is also enough for the water droplet to survive. So it is easier for solution droplet to survive rather than pure water droplet. This fractional reduction, the fractional reduction in the water vapor pressure is given by Raoult. E dash by E is equal to F, where E dash is the saturation vapor pressure, of water adjacent to solution droplet. E dash is the saturation vapor pressure of water adjacent to a solution droplet of mole fraction F. And E is the saturation vapor pressure of water adjacent to a pure water droplet. So E is the saturation vapor pressure of water So here we are comparing the saturation vapor pressure of the solution droplet with the saturation vapor pressure of a pure water droplet. What if the CCN didn't condense, didn't solve in the water? In that case, what will be the saturation vapor pressure? So that reduction is basically equal to the mole fraction. Reduction is basically equal to the mole fraction of the solution droplet. So that's what basically the Raoult's law says. So the mole fraction mole fraction of pure water is defined as number of moles per water in the solution divided by the total number of moles in the solution. Number of moles of pure water in the solution divided by the total number of moles, that is pure water plus the dissolved material. Mole fraction is defined as the number of moles per water in the solution divided by the total number of moles in the solution. So consider a solution droplet of radius r. Consider a solution droplet of radius r that contains mass m of a dissolved material. So we have a solution droplet. The size of the droplet is r. The mass of dissolved material is m, and the molecular weight of the material is basically ms. Molecular weight of the solute is ms. If each molecule of the material dissociates into I ions, so once it dissolves, it dissociates into ions. So each molecule dissociates into I ions. Effective number of moles of the material in the droplet is given by so each molecule gives I ions. So the effective number of moles of the material in the droplet will be, each mole gives I ions. The number of moles of the material is basically 1000 into m by ms, where m is in kilogram. So ms is in grams, so 1000 we are multiplying. So I into 1000, and this is number of moles of the dissolved material into I. If each mole is dissociating into I ions, then I into 1000 m by ms. M by ms gives the number of moles, mass in gram by molecular weight, and 1000 is to convert it into grams, since m is given in kilogram. Assume that the m is given in kilogram and ms is in gram. So 1000 into m by ms is the number of moles, and I is each mole is giving I ions. So this many number of moles are dissociating. I into 1000 m by ms is the effective number of moles of the material in the droplet. Now if the density of the solution so I into 1000 I into 1000 into m by ms is the effective number of moles. Effective number of moles of the Rho, the density is rho dash. Rho dash is the density of the solution, and the molecular weight is mW. Molecular weight of water. The number of moles of pure water. Number of moles of pure water will be 4 by 3 pi r cube rho dash minus n divided by n w. This is the mass of so this is basically the mass of the solution. 4 by 3 volume into density. This is the mass of the solution, and this is the mass of the dissolved material. So the mass of the solution minus the mass of the dissolved material gives you the mass of the water. So mass of water divided by the molecular weight gives you the number of moles of pure water. So 4 by 3 pi r cube rho dash minus n by capital MW is the number of moles of pure water in the solution. So now mole fraction, this is F, as we said earlier, F is basically so now if you want to find the mole fraction is basically the number of moles of pure water divided by the total number of moles of the solution. The number of moles of pure water divided by the number of moles of the solution. So we know the number of moles of pure water is basically 4 by 3 pi r cube rho dash minus m divided by mw whole divided by the number of moles of the solution. Number of moles of the solution is the total number of moles of water, pure water, plus the number of moles of the solute. That is the total number of moles of the solution. This is the number of moles of pure water, 4 by 3 pi r cube rho dash minus m divided by mw plus Im by ms. M is the mass of the solute, capital MS is the molecular weight, and I is the number of ions, that is in soluble form or in ion form, how many, the number of soluble particles in the solution is given by I into M by ms. This we can write it as 4 by 3 pi r cube rho dash minus m divided by mw plus Im by ms divided by 4 by 3 pi r cube rho dash minus m by mw, the whole inverse. We are just taking the inverse of the equation, which can be written as 1 plus Im mw divided by ms into 4 by 3 pi r cube rho dash minus m. So this by this will be 1. So 1 plus this by this will become Im mw by ms into 4 by 3 pi r cube rho dash minus m, the whole inverse. now we are comparing the energy equation that we obtained for curvature effect by replacing sigma and n by sigma dash and n dash to indicate the surface energy and number concentration of water molecules for the solution. So initially when we did so this is basically in case of E dash by change in the saturation vapor pressure of the solution with respect to the change in the saturation with respect to the saturation vapor pressure of pure water or pure water droplets is basically given by, we just got it as 1 plus Im mw divided by ms into 4 by 3 pi r cube rho dash minus m, the whole in, right? Now we combine the equation that we got for that droplet of radius r. It will become E dash. In that case, we got like E dash by Es is equal to exponential 2 sigma by n kT into r. Or RT we got, in the first case we got by 2 sigma by r rho L into RT we got r. In case of the curvature effect equation we got was Es as E by Es is equal to exponential of 2 sigma by r rho L into RV. So this is in case of a solution droplet. If we want to find the um, equation of the saturation vapor pressure adjacent to a solution droplet with a specified radius r. The saturation, this is for Raoult's law and this is for curvature. In this case, we haven't considered the curvature of the droplet that is formed. So saturation vapor pressure E dash adjacent to a solution droplet with a specified radius r. Just having a radius r. The specified radius r is given by E dash by E. Combine these two, we will get, due to the curvature effect, it will be exponential of 2 sigma dash to show that it is the solution that we are considering, rho L dash TRV into 1 plus IMMW by MS 4 by 3 pi r cube rho dash minus the whole. So this is in case of the saturation vapor pressure adjacent to a solution droplet which is having a specified radius r. We have combined both curvature and the okay. I think it is clear. So we learned what is homogeneous nucleation. What is homogeneous nucleation? heterogeneous nucleation with the help of an external particle when the water vapor condenses. It is known as heterogeneous nucleation. We learned like aerosols are there, and in aerosols there is a subset of aerosols as cloud condensation nuclei, which is basically hydrophilic in nature. Hydrophilic aerosols act as cloud condensation nuclei, and the cloud condensation nuclei, some are soluble and some are insoluble. So the droplet formation happens faster in case of soluble aerosols. And we learned about curvature effect. Higher the curvature of the droplet, the higher the saturation vapor pressure to maintain equilibrium. And we learned Raoult's law. Raoult's law basically says that the saturation vapor pressure of the solution droplet with respect to the saturation vapor pressure of a pure water droplet, there will be a fractional reduction in the saturation vapor pressure of water adjacent to a solution droplet compared to that of the saturation vapor pressure adjacent to a pure water droplet. There will be a fractional reduction in the water vapor pressure, and it is given by the mole fraction of the mole fraction of the pure water droplet. So F was given by E dash by E. Where E dash is the saturation vapor pressure adjacent to a solution droplet of F mole fraction, and E is the saturation vapor pressure of water adjacent to a pure water droplet. Raoult's law. Fractional reduction in the saturation vapor pressure adjacent to a solution droplet compared to that of the saturation vapor pressure adjacent to a pure water droplet. That is Raoult's law. Curvature effect basically shows you higher the curvature, higher the chance of evaporation. Higher the curvature, higher the chance of evaporation. So the higher the supersaturation required to keep the droplet molecule intact. So that is curvature effect. And we also derived the mathematical equation for both curvature effect and also for Raoult's effect. And we finally combine both. Now we will discuss one more topic. We will move on to another topic, which is basically like some properties of the ionosphere and the different layers and all those things. So ionosphere, we know we have learned about the different layers in the atmosphere, starting from troposphere, stratosphere, mesosphere, and thermosphere. So ionosphere basically starts from the upper region of mesosphere and then extends towards the thermosphere. So this is the region of the Earth's atmosphere where electrons and ions are present in large numbers. So over this region in the Earth's atmosphere, electrons and ions. So generally we have molecules, the gases in the form of molecules in the atmosphere. But when we reach the ionosphere, here the Earth's atmosphere consists of a large number of electrons and ions, and these since it is present in large numbers, they are capable of influencing the radio wave propagation as well. So this region, the ionosphere, ionosphere is a region where a large number of electrons and ions are present. This extends from around 60 km to 400 km in the atmosphere, and it starts from mesosphere and goes to thermosphere. When we look at the different layers in the atmosphere, it basically starts from the mesosphere and it extends to the thermosphere or exosphere. And this layer, this region has different sub-layers, which is basically known as the D region. First layer is a D region. It basically extends from 60 to 100 km. the lowermost layer is the D region. It extends from 60 to 100 kilometers. And above the D region, we have the E region. So three different layers are there: D, E, and F. So D is the lowermost layer. It extends from 60 to 100 kilometers. Then we have the E region, which extends from 100 to 150 kilometers. Then there is the F region, which is again divided into two. So this is D, this is E, then F is there. F is again divided into two, which is F1 and F. So F1 extends from 150 to 250 kilometers, and F2 is above 250 kilometers, known as the F2 region. So these are the four different layers in the atmosphere. So ionosphere is a layer in the atmosphere where a large number of electrons and ions are present. It basically from it basically starts from mesosphere and goes to thermosphere, extends till thermosphere. Starts from mesosphere and extends till thermosphere. And it has four different sublayers: E, D, E, F1 and F2. D is the lowermost layer, which extends from 60 to 100 kilometers. Then we have E, which extends from 100 to 150. Above that there is F1 and F2. F1 extends from 150 to 250, and F2 extends from F2 is greater than 250. So these are the four different regions in the ionosphere. So as you can see, so this basically shows you the altitude and the electron density. So as I said, this is the layer in the atmosphere where large number of electrons and ions are present. So different layers in the ionosphere are basically determined, or they are basically classified based on the amount of electrons, or the electron density present in each layer. So whenever there is inflection or turnover in the electron concentration, then it is classified as a particular layer. So it is not. So basically, based on the peak production and rate of ions, peak production or rate of ions, this profile is basically drawn based on the amount of electron, or the number of electrons that is produced in each layer. This profile is drawn, and there is inflection or turnover point that is defined as each layer. As we can see, D region starts from here till here. Then there is a sudden change in the slope of the curve over this region. Then the next second region starts. Then again the curve is smooth. Then again here some inflection is happening. So there the second layer is starting. So whenever there is inflection or turnover, so those are defined as the boundaries between different layers. So the peak production, peak ionosphere, peak production of electrons in the ionosphere basically occurs as the production of electrons and ions. Production peaks at the production of ions or electrons peaks at 250 kilometers. Above and below that layer, around here the production of electrons peak. Above and below the concentration is less. The concentration of electrons is less. This is where it peaks. So basically, why it is peaking at this height? So basically, we know how the electrons and ions. Initially, we will just see how this electrons and ions are produced. So basically, the radiation from the sun at shorter wavelengths causes photoionization of atmosphere, resulting in partially ionized region called the ionosphere. So when the sun's radiation is coming, the sun's solar radiation at shorter wavelengths cause photoionization of the atmosphere. we know that this is very much close to the sun. Like this is the topmost layer. There is the mesosphere and thermosphere. These are the topmost layers. So because of the solar radiation of shorter wavelengths or very strong solar radiation that is reaching this region, the atmospheric molecules present over this region is partially ionized, and which basically results in the formation of ionosphere. So what does it mean by photoionization? The atoms or molecules present in this layer plus interact with the incoming solar radiation, produce ions plus electrons plus energy. The incoming solar radiation at shorter wavelengths results in the ionization of or causes the ionization of the atoms or molecules present in these topmost layers. So why this maximum is happening at a height of 250 kilometers? So we know that the result for the formation, the reason for the formation of these ions are basically the incoming solar radiation. The higher incoming solar radiation will be present in the topmost or the higher levels in the ionosphere. So incoming solar radiation should be there, and also there should be enough atoms or molecules to undergo ionization. So we know that as we go up in the atmosphere is becoming rarer and rarer. That means the concentration of atoms and molecules is reducing as we go up in the atmosphere. So both are kind of the value, both incoming solar radiation and atoms of, so it is having a kind of opposite profile. As we come down, as we go up as we go up in altitude, the amount of the intensity of solar radiation is increasing, whereas the concentration of atoms or molecules is decreasing. So around 250 kilometer, both are kind of high, or it is kind of in between, and that's why around 250 kilometer we are getting a maximum. This peak is maximum because above that layer, if we go, there will be very less, even though there is very high intensity of solar radiation is there, the concentration of atoms or molecules will be very less. That's why if we go above it, the production is decreasing, and also if we come below 250 kilometer, also the production is increasing. That decreasing, it may be because as we come down to 50 kilometer, even though there is enough concentration of atoms or molecules in the atmosphere, the intensity of solar radiation that is reaching this lower layers are decreasing. So maybe that's why we are getting a peak production at height of 250 kilometers. And some more like characteristics of these different layers. So the D region is extended from 60 to 90 kilometers. The peak production height is around 90 kilometers, and the density, the electron density is 10 raised to 8 to 10 raised to 10 per meter cube. This is the lowermost layer, and we can see as we go up, the production is increasing. The density of the electrons is increasing. This is because of the availability of more intense solar radiation in the higher levels. And E is the second layer where the altitude, it is extending from 90 to 150 kilometers, and the peak production is happening at a height of around 110 kilometers. The electron density is around 10 raised to 11 per meter cube. Then we have the two regions which are F1 and F2. F1 is the lowermost F layer, which is extending from 140 to 200 kilometers. The peak production is happening at a height of 200 kilometers, and the electron density is 10 raised to 11 to 10 raised to 12 per meter cube. Then we have the F2 layer, which is extending from 200 to 500 kilometers. The peak production is happening at a height of 300 kilometers, and the density of the electron is around 10 raised to 12 per meter cube. So these are the four different layers. Now, as I told you, the ions and the ionosphere is basically formed because of the process of photoionization of the atoms or molecules present in the atmosphere by the incoming solar radiation. So, since the main source or main reason is photoionization, it should obviously have a diurnal variation when there is availability of sunlight and when there is no availability of sunlight. So, daytime and nighttime, this different layers in the ionosphere is having different structure. The ionosphere is having a different structure in daytime and nighttime. So daytime there is enough sufficient availability of solar radiation. So more photoionization takes place. There is more distinct. All four layers are present very distinctly. Whereas during nighttime there is no availability of solar radiation. So the many of the layers disappear and the layers become less distinct and weaker. So during daytime, all layers have high electron density because solar radiation is strong. And during night, solar radiation is not there. The energy that is produced during the photoionization that is happening during daytime helps in further ionization. What happens at night? The D and F1 disappears. The lower layer and the F1 disappears at night, and E and F2 becomes weaker. So during night time only two layers are present, E and F2. D and F1 disappears because there is no solar radiation available. Now similar to this diurnal radiation, the solar, based on the solar cycle also, it shows these layers have different behavior. The beginning of the solar cycle, the sunspots will be minimum. The middle of the solar cycle, the number of sunspots are maximum. So this basically shows the different profiles of the ionosphere during solar maximum, solar minimum, and also daytime and nighttime. So these two, this one and this one, corresponds to solar maximum. So these two lines corresponds to solar maximum, and these two lines corresponds to solar minimum. Both daytime and nighttime are also there. As you can see, the daytime solar minimum. So when there is solar minimum, that is this one. Solar minimum daytime is this line. The daytime solar minima is actually less than the nighttime solar maximum. So when the solar minima is going on, or the sunspots is the sunspots are minimum, in that case, even if it is daytime, the values are less than the nighttime solar maximum. Solar maxima nighttime is this one. Solar maxima nighttime. So daytime solar minima is less than nighttime solar maximum. So when the solar maximum is going on, even the nighttime production is greater than the daytime production during solar minimum. So, similar to the diurnal variation, the cycle of this solar maximum, the sun cycle or the solar cycle also matches. of the electrons. Like we will just look at the different layers in a more detail, the different layers of the ionosphere in a much detailed way. So we saw that the layer, first the lower most layer is the layer. The lowest region in the atmosphere. The height is 50 to 90 kilometers. This region is produced using Lyman seeds, which basically means alpha radiation with lambda is equal to 121.6 nanometers. Solar radiation that is having a wavelength of 121.6 nanometers is basically leading to the production or leading to the production of this particular region. So this is very weakly ionized because since this is the lowermost layer, most of the energy is absorbed in the upper layers. The daytime density is around 10 raised to 8 to 10 raised to 10 electrons per meter cube. And this disappears during nighttime. The D layer disappears during nighttime. This is generally produced due to the ionization of nitrogen oxide, NO. Peak production happens at 70 to 95 units. That is about the D layer. If we look at the E layer, second layer, it is at a height of 90 to 140 kilometers. These are produced by X-rays 1 to 10 nanometer radiation and the UV radiation. X-rays and UV is 100 to 150 nanometer. And this is mostly produced by the ionization of oxygen molecules. Ionization of oxygen or NO2, nitrogen. Daytime electron production ten raised to 11 electrons per meter cube. And this also this also begins to disappear at night, or it becomes weaker at night, but it doesn't. It is very weak. It is there. It doesn't disappear completely, but it is very weak. D region completely disappears at night, but E is still there, but it will be very weak. Begins to disappear at night, but not completely. Now the uppermost layers F1 and F2. F layer, we have F1, this is the lower F layer. The height is from 140 to 200 kilometers. Electron density is around 3 into 10 raised to 11 electrons per meter cube. Then it is mostly formed by the ionization of oxygen atoms by extreme UV radiation. Then the F2 layer is there. This is the upper F layer. It is at a height of greater than 250 kilometers. The electron density over this region is 2 into 10 raised to 12 electrons per meter cube. This is the highest and the topmost layers. So these are the basics about the ionosphere and its different layers, how it is produced, what is peak production, what is the electron density of different layers, etc. I think we will wind up for today. If you have any doubt, you can ask. We will start.